May 11th, 1945. Radar Picket Station Number 15, 50 miles north of Okinawa. Commander Albert Hall gripped the plotting table aboard the destroyer USS Hugh W. Hadley, as the radar screen painted a nightmare. 156 incoming contacts. Japanese aircraft converging from multiple directions in what would become the largest concentrated air attack against two American ships in the entire Pacific War. Hall's executive officer looked at him with the unspoken question hanging between them. They were alone, 2 destroyers and 4 support gunboats against more than 150 suicide aircraft. The mathematics were simple and brutal. If conventional anti-aircraft fire required 2,500 rounds to down a single aircraft, they would run out of ammunition long before they ran out of targets. But Hall knew something the approaching Japanese pilots did not. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Every 5-inch shell in Hadley's magazines was fitted with a fuse that would rewrite those mathematics. A proximity fuse that detonated automatically within 70 feet of an aircraft. The Japanese had been dying to this technology for 2 years without understanding what was killing them. The morning of January 5, 1943, Kula Gulf, Solomon Islands, had marked the beginning. Lieutenant Red Cochran commanded the after 5-inch battery aboard the cruiser USS Helena when 4 Aichi D-3A dive bombers completed their attack run against the American task force. These Val dive bombers had struck the New Zealand cruiser Achilles and were turning away with the practiced precision Japanese naval aviators had perfected through years of combat. Cochran's gun crew tracked the departing aircraft. 2 salvos thundered from Helena's after battery. One of the Japanese aircraft erupted in flames without being touched by a direct hit. The shell had exploded 30 feet from the target, ripping the aircraft apart with a cone of shrapnel that no pilot could evade, and no aircraft could survive. The pilot never understood what killed him, neither did his formation leader, who witnessed the destruction. Neither would Japanese Imperial Headquarters for the remainder of the war. This was the first combat kill by a weapon that military historians would later rank alongside radar and the atomic bomb in strategic importance. The proximity fuse, deceptively codenamed the variable time or VT fuse, had just announced itself to the Pacific War. Over the next 2.5 years, this technology would fundamentally alter Japanese tactical calculations, shatter their aerial offensive capability, and save thousands of American lives. But the transformation began not with American brilliance. It began with a fundamental problem that had plagued anti-aircraft gunners since aircraft first became weapons of war. December 7, 1941, Pearl Harbor, Oahu, Hawaii. As Japanese aircraft screamed through tropical skies that Sunday morning, American gun crews fought back with everything available. 5-inch naval guns thundered from damaged battleships and cruisers, hurling shells skyward at attacking dive bombers and torpedo planes. Each shell required manual fuse setting, a sailor physically turning a wrench against a clockwork mechanism while enemy aircraft dove through defensive fire, adjusting the timer that would determine when the shell exploded. Most shells detonated harmlessly in empty sky, their preset timers triggering them seconds too early or too late. Some never exploded at all, their mechanical fuses failing under the stress of launch. Others fell back to Earth, still armed, their contact fuses ready to detonate on impact. In Honolulu, 9 miles from the harbor, 55-pound shells crashed through roofs, detonated in streets, tore through buildings. The Hayasaki family died when a 5-inch shell flew through their restaurant window during breakfast service. Father Jitsuo, sons Jackie and Robert, daughter Shirley, and nephew George perished instantly, along with 7 young customers eating at the Cherry Blossom restaurant that morning. 3-month-old Janet Yumiko Ota became the youngest casualty when a shell struck her home, killing her, her mother, and her aunt. By the time smoke cleared over Pearl Harbor, 68 civilians lay dead. 32 of them had been killed not by Japanese bombs but by improperly fused American anti-aircraft shells landing in the city 9 miles away. The tragedy illustrated with brutal clarity the inadequacy of existing technology against modern aircraft. The mathematics were unforgiving and had been since the Great War. Traditional anti-aircraft fire required 3 pieces of perfect information executed in sequence under combat conditions. First, optical rangefinders had to calculate exact distance to a target moving at 300 miles per hour, potentially through smoke, clouds, or tropical sun glare. Second, height-finding equipment had to estimate altitude against fast-moving targets that could climb or dive at will. Third, fire control computers had to calculate where the aircraft would be in the 15 to 30 seconds it took a shell to reach that altitude. A sailor then manually set a clockwork time fuse using a specialized wrench. The shell was loaded, the gun fired, and the fuse mechanism counted down its preset time during flight. If all calculations were perfect, if the aircraft maintained course and speed, if the mechanical fuse functioned correctly, the shell would explode near the target. The odds of destroying an aircraft were approximately 1 in 2,500 rounds fired under ideal conditions. In actual combat with multiple targets maneuvering through defensive fire, the odds dropped catastrophically. The problem had existed since the First World War, but became critical as aircraft evolved. In 1918, aircraft flew at 90 miles per hour at altitudes below 15,000 feet. By 1940, modern fighters exceeded 400 miles per hour at altitudes above 30,000 feet. The gap between gunnery technology and aerial performance had widened into a chasm that no amount of training could bridge. The British discovered this reality facing German dive bombers over Dunkirk in 1940. Ships lacked space for additional guns. More ammunition consumed limited magazine space. Better fire control computers helped but could not overcome the fundamental limitation of time fuses requiring perfect prediction of an aircraft's future position. And prediction was impossible when pilots could see shells exploding and maneuver to avoid the next salvo. August 1940. The Department of Terrestrial Magnetism, Carnegie Institution, Washington, District of Columbia. Dr. Merle Anthony Tuve received an assignment from the National Defense Research Committee that most scientists would have considered impossible. Born in South Dakota, educated at the University of Minnesota and Johns Hopkins, Tuve had spent his career exploring the physics of the ionosphere using radio waves. In 1925, working with Gregory Bright, he had pioneered techniques for measuring the reflection of radio waves from the ionosphere to map its structure. This work laid theoretical foundations that would later enable radar development. When the committee approached him about developing a proximity fuse for artillery shells, he understood immediately that radio physics might provide the solution others had sought for decades. The British had shared preliminary research during the Tizard mission, concluding that while a proximity fuse might work in rockets or bombs, the forces involved in artillery made it impossible for conventional shells. A 5-inch shell experienced acceleration of 20,000 times the force of gravity when fired. No electronic device known in 1940 could survive such forces, certainly not the delicate vacuum tubes that formed the only available electronic components. Tuve proposed something that seemed equally impossible. A miniature radio transmitter and receiver no larger than a pint milk bottle installed in the nose of an artillery shell. The transmitter would broadcast continuously as the shell flew toward its target. As the shell approached an aircraft, radio waves would reflect back from the metal surface. The frequency of the reflected signal would shift due to the Doppler effect, the same phenomenon that makes a train whistle change pitch as it passes. When the frequency shift reached a predetermined level indicating proximity to the target, an electronic circuit would close, sending current to a detonator that would explode the main charge. Simple in concept. Impossible in execution given the technology of 1940. Every component presented problems that seemed insurmountable. The project, designated Section T of the National Defense Research Committee, began on August 24, 1940, with Tuve as chairman and a handful of researchers in a laboratory at the Carnegie Institution. Their first challenge was identifying what components a working fuse required. A radio transmitter capable of operating at frequencies that would provide usable Doppler shift, a receiver sensitive enough to detect reflected signals from an aircraft several hundred feet away, an electronic amplifier to boost the received signal, a circuit to compare transmitted and received frequencies and detect the Doppler shift that indicated closing distance, a power source that could provide sufficient voltage and current, a detonator triggered by the electronic circuit, safety mechanisms to prevent premature detonation during handling or storage. All of this had to fit inside a space approximately 8 inches long and 2 inches in diameter, the standard dimensions of a shell nose fuse. Every component needed to function in extreme temperatures, ranging from Arctic cold to tropical heat, and survive storage for months in ammunition magazines. Most daunting of all, everything had to withstand the shock of being fired from a gun. Vacuum tubes, the only electronic amplifying devices available in 1940, were fragile glass envelopes containing delicate filaments and electrodes separated by thousandths of an inch. Standard radio tubes were 6 inches tall and weighed several ounces. The largest tubes manufactured for rugged applications were designed for mobile military radios and could withstand 10 times the force of gravity during transport over rough terrain. The fuse required tubes that could survive 20,000 times the force of gravity. At 20,000 G, a 1-ounce tube would effectively weigh 1,250 pounds for the fraction of a second it took the shell to travel down the barrel. Forces sufficient to turn solid steel components into fragments. The shell then spun at 25,000 revolutions per minute as rifling imparted stabilizing rotation. October 1940. Laboratories across America received urgent requests from the National Defense Research Committee. Western Electric Company and Radio Corporation of America were asked to develop miniaturized vacuum tubes hardened for extreme acceleration. Sylvania developed specialized glass formulations with additives that increased strength while maintaining the vacuum seal necessary for tube operation. Raytheon experimented with tube designs featuring planar electrodes that distributed forces more evenly than conventional structures. Engineers discovered that conventional assembly techniques produced tubes that shattered instantly under high acceleration. The solution required innovations in every aspect of tube design and manufacturing. Glass composition was modified with additives that increased tensile strength. Internal components were embedded in shock-absorbing materials that cushioned them during the violence of launch. Electrode structures redesigned using spot welding techniques that created mechanical bonds capable of surviving extreme stress without separation. Through spring and summer of 1941, after thousands of design iterations and countless failures, acceptable tubes emerged from production lines measuring less than 1 inch in height and capable of surviving 20,000 G acceleration. Testing was brutal. Prototype fuses were loaded into shells and fired from a vertical gun at the Naval Proving Ground in Dahlgren, Virginia, into soft earth that allowed recovery. Engineers examined each tube under microscopes to identify failure modes, then redesigned and tested again. The power source presented equally daunting challenges. Conventional batteries were too large and had limited shelf life, particularly in the tropical heat of the Pacific Theater, where temperatures inside ammunition magazines could exceed 130 degrees Fahrenheit. Harry Diamond and Wilbur Hinman at the National Bureau of Standards developed an ingenious solution. A glass tube filled with electrolyte solution, sealed with metal plates at each end. When the shell was at rest, the liquid remained in the center of the tube, isolated from the metal plates by simple gravity. When fired, centrifugal force from the shell's spin drove the electrolyte outward against small pieces of reactive metal embedded in the tube walls. Chemical reaction between the electrolyte and metal plates generated electrical current sufficient to power the radio circuits. The battery activated only when the shell was spinning at high velocity, providing a built-in safety mechanism that prevented premature detonation during handling or storage. This reserve battery design gave the fuses indefinite storage life, solving a problem that had plagued earlier attempts at electrical fusing systems. May 6, 1941. Dahlgren Naval Proving Ground, Virginia. 6 prototype fuses built by the National Bureau of Standards team were loaded into air-dropped bombs and tested over water. Radio transmitters activated during fall. Receivers detected reflections from the water's surface approaching at increasing velocity. Electronic circuits triggered detonators at the preset altitude. All 6 bombs exploded at the correct height above the Potomac River. The success validated the basic concept, but bombs experienced only a few hundred times the force of gravity when released from aircraft. Artillery presented a challenge 2 orders of magnitude greater. By June 1941, Section T had expanded to over 100 engineers, physicists, and ordnance specialists working in conditions of absolute secrecy. A former automobile dealership in Silver Spring, Maryland, became the main laboratory, with security so strict that neighbors speculated endlessly about the mysterious activities behind blackout curtains. The cover story described research into optical instruments for fire control systems. The reality was a crash program to develop a weapon that Allied military leaders believed could alter the course of the war before America was even formally engaged. The development process revealed cascading engineering challenges that required solutions to problems no one had previously attempted to solve. The antenna had to be small enough to fit in the nose cone, while efficient enough to transmit and receive radio signals at frequencies around 80 MHz. Engineers developed a ring antenna circling the fuse body, elegant in its simplicity but requiring precise tuning. The transmitter circuit had to generate radio frequency signals stable enough for Doppler detection, using just 3 miniature vacuum tubes. Circuit designers created transmitter designs that operated reliably despite the thermal shock of launch and the extreme vibration environment inside a spinning shell traveling at 2,600 feet per second. The receiver circuit had to detect signals 1/millionth the strength of the transmitted signal and amplify them sufficiently to trigger the detonation circuit. Amplifier stages using 4 vacuum tubes provided sufficient gain while maintaining stability. The Doppler detection circuit compared transmitted and received frequencies, closing an electrical contact when the difference indicated proximity to a target approximately 70 feet away. December 1941. The attack on Pearl Harbor transformed the proximity fuse project from important research to the highest national priority. The Navy had been skeptical that electronics could survive gun launch forces. Witnessing the complete inadequacy of time fuses during the Pearl Harbor attack, with friendly fire casualties exceeding those of some enemy raids, eliminated all doubts about the need. Production contracts expanded from millions to hundreds of millions of dollars overnight. Johns Hopkins Applied Physics Laboratory was founded on March 10, 1942, specifically to centralize proximity fuse development under one roof. 5 companies received contracts to mass-produce fuses following designs developed at APL. Crosley Corporation in Cincinnati, RCA, Eastman Kodak, General Electric, and McQuay Norris committed entire factory buildings to fuse production. Over 100 factories would ultimately participate in some phase of component manufacturing. Each complete fuse contained approximately 130 miniaturized parts, each manufactured to tolerances measured in thousandths of an inch. The goal was 40,000 fuses per day by late 1943, 70,000 per day by war's end, an industrial undertaking second only to the Manhattan Project in complexity and cost. The secrecy surrounding the project was absolute and multi-layered. Workers assembling components never knew what the final product would do, or even that other factories were building identical items. Different companies manufactured different sub-assemblies that were brought together only at final assembly plants. The designation variable time fuse was chosen specifically to mislead anyone who might learn of the project into believing it was simply an improved mechanical timer. The code word POSIT was used in military communications. Even after combat use began, captured fuses that failed to detonate were examined by Japanese and German engineers who assumed they were some kind of advanced mechanical time fuse. The possibility that they contained miniature radio transmitters seemed beyond credible technology. This failure of enemy imagination would prove as valuable as any security measure. August 12, 1942. Chesapeake Bay, Virginia. The cruiser USS Cleveland conducted the first comprehensive test of production proximity fuses against drone aircraft that simulated enemy attack profiles. 3 radio-controlled target drones were launched from a nearby airfield to fly attack patterns against the anchored cruiser. Cleveland's 5-inch gun crews had been trained on the new ammunition, but not told how the fuses functioned. They knew only that these shells did not require manual time setting, and that they should fire them exactly as they would conventional ammunition. The first drone approached at 12,000 feet. Cleveland's forward battery engaged. The first salvo missed. The second salvo produced a spectacular mid-air explosion as one shell detonated near the drone, shredding it with fragments. The drone tumbled from the sky in pieces. The gun crew stood silent for a moment, processing what they had witnessed. They had destroyed an aircraft with fewer than 10 rounds. The second and third drones lasted no longer. Naval observers cancelled the remainder of the 2-day test schedule immediately and authorized emergency mass production and fleet deployment. In previous tests over 2 years of development, time-fused shells required an average of 2,500 rounds fired per aircraft, destroyed under controlled conditions. Proximity-fused shells were destroying drones with single salvos, demonstrating better than 25-fold improvement in effectiveness. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The implications were staggering. Ships could carry the same ammunition load but destroy 25 times as many attacking aircraft, or achieve the same defensive effectiveness while firing a fraction of the ammunition, conserving magazine space for other missions. Production accelerated through fall 1942, despite enormous technical challenges. The first combat-ready fuses reached fleet units in October, carefully distributed to prevent accidental disclosure if ships were damaged or sunk. The cruiser Helena received 500 rounds of proximity-fused 5-inch ammunition, stored separately from conventional ammunition with strict orders. Instructions emphasized that proximity fuses were to be used only over water, where duds would sink beyond enemy recovery. Gunners received training but were not told how the fuses functioned, only that they were highly classified and represented a significant tactical advantage. Initial fleet reaction ranged from skepticism to curiosity. Sailors who had survived Pearl Harbor and subsequent engagements had little faith that any technology could substantially improve anti-aircraft effectiveness. The morning of January 5, 1943, resolved all doubts permanently. Lieutenant Cochrane's salvos from Helena destroyed one Val dive bomber completely and damaged a second badly enough that it crashed attempting to return to base. The gun crew had achieved what previous technology made nearly impossible. They had killed aircraft without perfect prediction of target position, without manual fuse setting, without the complex calculations that had limited anti-aircraft effectiveness since its inception. Word spread through the Pacific Fleet with remarkable speed despite classification restrictions. Ships that had received proximity fuses began using them in every engagement over water. Cruisers, destroyers, and battleships reported kill ratios that far exceeded anything achieved with time fuses under identical circumstances. Enemy pilots noticed something had changed in American defensive fire, but could not understand the nature of the improvement. By March 1943, 25% of all anti-aircraft ammunition issued to Pacific Fleet units contained proximity fuses. These rounds accounted for over 50% of all Japanese aircraft destroyed by naval gunfire during that period. Statistical analysis showed proximity fuses were approximately 3 times more effective per round than conventional time fuses under identical conditions against fast-moving targets. In night engagements where visual tracking was nearly impossible and time fuses were largely ineffective, the advantage increased to 7-fold. Ships previously dependent on creating walls of steel through sheer volume of fire could now achieve decisive aerial kills with a fraction of the ammunition expenditure. The effectiveness of proximity fuses triggered Japanese tactical changes that Allied intelligence observed but could not initially explain through intercepted communications. Japanese aircraft began attacking from higher altitudes, where their bombing accuracy suffered, but they remained outside the most effective range of ship defenses. Torpedo bombers approached at wave-top altitude, where radio reflections from the ocean surface sometimes caused premature fuse detonations, though this tactic made them vulnerable to automatic weapons fire. Dive bombers released at steeper angles and higher speeds to minimize exposure time to defensive fire, sacrificing the precision that had made them so effective earlier in the war. These adaptations reduced Japanese strike effectiveness significantly, while failing to restore the tactical advantage they had enjoyed during 1941 and early 1942. American ships continued shooting down Japanese aircraft at rates that made conventional attacks operationally unsustainable. Admiral William Halsey, commanding major fleet operations in the South Pacific, credited proximity fuses with fundamentally changing the balance of naval-air warfare. Japanese torpedo bombers, which had been particularly effective in night attacks when visual tracking was difficult and time fuses nearly useless, now faced destruction rates exceeding 50%, even in total darkness, when ships combined radar detection with proximity-fused ammunition. During 1943, despite using proximity fuses in only 25% of total ammunition expended, over half of all Japanese aircraft destroyed by anti-aircraft fire fell to proximity-fused shells. This disproportionate effectiveness reflected both the superior performance of the technology and the tactical situations where commanders chose to employ their limited supply of the advanced ammunition. October 1944. The Philippines Campaign. Japanese forces facing inevitable strategic defeat implemented a tactic that would test American defenses to their absolute breaking point. Special attack units, officially termed Shinpu Tokubetsu Kogeki Tai but known universally by the word kamikaze, began organized suicide attacks against American naval vessels. The first systematic kamikaze attacks struck during the Battle of Leyte Gulf in late October. The tactic emerged from desperation and Japanese recognition that conventional attacks had become devastatingly ineffective against American ships equipped with radar, fighter direction, and proximity fuses. Experienced pilots had been systematically destroyed over 2 years of attrition warfare. Replacement pilots received minimal training, sometimes as little as 40 hours of flight time, insufficient for the precision required in bombing and torpedo attacks. Kamikaze attacks required only enough skill to keep an aircraft pointed at a target and dive at tarm, maximum speed. No need to line up a bombing run, calculate lead angles, or execute a torpedo drop. No need to escape after the attack. The pilot himself became the guidance system, able to make final corrections that no bomb or torpedo could match. Proximity fuses proved essential against kamikaze attacks, though their effectiveness was complicated by the fundamental nature of the threat. Conventional attacks saw aircraft approach, release weapons, and attempt to escape. Proximity fuses destroyed attackers at distances where damaged aircraft would tumble harmlessly into the sea, their weapons falling short of targets. Kamikaze attacks eliminated the escape phase entirely. Pilots flying damaged aircraft, sometimes with wings shredded and engines aflame, continued toward targets with fanatical determination. Aircraft that would have caused conventional attackers to abort remained airborne long enough to crash into ships, even after sustaining damage that destroyed control surfaces and killed pilots. The solution required concentration of fire that destroyed aircraft completely, rather than merely damaging them. Ships increased rates of fire, creating denser patterns of proximity-fused shells, and engaged targets at longer ranges to allow multiple salvos before aircraft closed to ramming distance. Gun directors tracked multiple targets simultaneously, prioritizing those with clearest approach paths to the ship. The mathematics of kamikaze defense were brutally simple. A conventional attacker damaged at 3,000 yards would likely abort. A kamikaze damaged at 3,000 yards had 15 seconds of flight time remaining before impact. Only complete destruction guaranteed safety. Proximity fuses provided the kill radius necessary for reliable destruction, but required multiple hits as insurance against the possibility that a damaged aircraft might remain controllable. Statistical analysis from late 1944 showed that ships using proximity-fused ammunition exclusively achieved kamikaze destruction rates above 60% when aircraft came within gun range. Ships using conventional time-fused ammunition achieved destruction rates below 20%. The difference represented the margin between survival and catastrophic loss. May 11th, 1945. USS Hadley and USS Evans, operating as radar picket ships 50 miles north of Okinawa, faced what naval historians would later identify as the most intensive air attack against such a small force in the Pacific War. Operation Kikusui No. 6 sent 156 aircraft against radar Picket Station No. 15. Hadley's radar detected the first contacts at 40 miles. Commander Hall ordered general quarters and notified the Combat Air Patrol of incoming raids. 4 Marine Corsairs responded, but 4 fighters against 156 attackers represented mathematical impossibility. The fighters would account for perhaps a dozen kills before being overwhelmed or running out of ammunition. The defense would depend on shipboard guns and the proximity fuses that armed every 5-inch shell in the magazines. The first wave struck at 8:45 in the morning. Japanese aircraft came from multiple directions simultaneously, a coordinated attack designed to saturate defenses and guarantee that some aircraft would penetrate to ramming distance. Hadley's 5-inch batteries engaged at maximum range, firing proximity-fused shells that created airbursts across the approach paths. The first aircraft disintegrated at 4,000 yards when 3 shells detonated simultaneously within 70 feet, creating overlapping fragment patterns that shredded the bomber. The second aircraft exploded at 3,500 yards, the third at 3,000 yards. Gun crews worked with desperate efficiency, loading and firing as fast as mechanisms allowed. The 5-inch guns could fire 15 rounds per minute under ideal conditions. In combat, with crews working at maximum speed and adrenaline-overwhelming fatigue, they sustained 18 rounds per minute. Each gun became a stream of proximity-fused shells, creating a barrier of airbursts that destroyed aircraft with mechanical precision. But 156 aircraft attacking over 90 minutes meant aircraft arrived faster than guns could destroy them. The Combat Air Patrol accounted for additional kills, but the mathematics remained impossible. Hadley destroyed 12 aircraft before the first kamikaze penetrated the defensive fire. The aircraft, already damaged by fragments from a near miss, crashed into the ship's superstructure, exploding on impact. Seconds later, a second kamikaze struck amidships. Then a third hit the fantail. A fourth aircraft, completely engulfed in flames from proximity fuse hits, remained airborne long enough to crash into the forward superstructure. Each impact brought fire, structural damage, and casualties. Yet Hadley's guns never stopped firing. USS Evans, 1,500 yards distant, faced similar overwhelming numbers. Her gun crews destroyed 23 attacking aircraft during the engagement, an almost incomprehensible achievement given the sustained intensity of the assault. But the sheer numbers guaranteed penetration. Evans absorbed 4 kamikaze hits that left her dead in the water, her engineering spaces flooded, her guns still firing on local control as central fire control was knocked offline. When the attack finally ended at 10:15 in the morning, both destroyers remained afloat despite catastrophic damage. Hadley had been hit by 1 bomb and 3 kamikaze aircraft. Evans had sustained 4 kamikaze impacts, yet both ships survived, were towed to safety, and eventually returned to service after extensive repairs. Post-action analysis documented the indispensable role of proximity fuses in the engagement. The 2 destroyers and 4 support gunboats had fired approximately 3,000 rounds of 5-inch ammunition during 90 minutes of continuous combat. This ammunition, almost entirely proximity fused, had destroyed or damaged over 40 Japanese aircraft confirmed by visual observation, likely more that fell beyond visual range or crashed attempting to return to bases. Without proximity fuses, analysts calculated that Hadley and Evans would have exhausted their ammunition within 30 minutes, while achieving perhaps 8 to 10 kills. Both ships would certainly have been sunk in the first hour of the attack, overwhelmed by aircraft their guns could not effectively engage. The proximity fuse had not made the ships invulnerable. It had made survival possible against mathematically impossible odds. The action off Okinawa demonstrated what American naval forces had learned through 2 years of combat experience with proximity fuses. The technology provided the kill radius necessary to destroy modern aircraft reliably, but it required doctrine, training, and tactics that maximized its effectiveness. Ships practiced air defense drills until gun crews could engage targets with mechanical efficiency, even under the stress of kamikaze attack. Fire control procedures prioritized targets that posed the greatest threat. Multiple ships coordinated their fire to create overlapping defensive zones, and commanders accepted that some aircraft would penetrate even the best defenses, requiring damage control teams as skilled as gun crews. Between October 1944 and August 1945, American naval forces operating around Okinawa and the Japanese home islands destroyed more than 2,800 Japanese aircraft using proximity-fused ammunition. Analysis by Dr. Ralph Baldwin in his authoritative post-war study showed that only 460 would have been destroyed using conventional time fuses under identical circumstances, representing a 6-to-1 effectiveness ratio. This advantage translated directly to lives saved and ships kept in action. At Okinawa, where American naval forces faced the most intensive kamikaze operations of the entire war, proximity fuses accounted for a significant percentage of Japanese aircraft destroyed by ships' guns, though the majority of overall kills still came from combat air patrols flying defensive circles around the fleet. The human cost to Japanese naval aviation was devastating and unsustainable. Japan lost over 12,000 aircraft in combat during the Pacific War. Documented evidence shows proximity fuses directly destroyed several hundred through anti-aircraft fire, but the broader impact extended far beyond direct kills. Each aircraft destroyed represented not just material loss but trained aircrew impossible to replace, given Japan's deteriorating training infrastructure. The death of experienced pilots in 1943 and 1944 forced Japan to commit poorly trained replacements who fell victim to American defenses at catastrophic rates. By early 1945, Japan resorted to kamikaze tactics, partly because conventional attack methods had proven completely ineffective against American ships equipped with proximity-fused ammunition, radar fire control, and coordinated fighter direction. Japanese aviators flying conventional bombing missions faced destruction rates exceeding 70% when attacking well-defended targets. These losses were operationally unsustainable. Kamikaze attacks, while horrific in their human cost, at least guaranteed that aircraft reached targets if they could penetrate defensive fire. The proximity fuse had made conventional Japanese naval aviation tactics obsolete. While proximity fuses revolutionized naval warfare in the Pacific, strict restrictions had prevented their use over land, where unexploded fuses might fall into enemy hands and reveal the technology to Axis engineers. German technical intelligence had proven remarkably capable of reverse engineering captured Allied equipment. The risk that Germany might develop their own proximity fuses and equip anti-aircraft defenses around strategic targets seemed unacceptable. But in June 1944, Germany's Von flying bomb campaign against London forced reconsideration of that absolute restriction. Beginning June 13th, Germany launched thousands of Von cruise missiles at England, sometimes exceeding 120 per day at the height of the assault. These pilotless aircraft, powered by pulse jet engines, traveled at 400 miles per hour at altitudes below 2,000 feet. Traditional anti-aircraft defenses struggled desperately against targets moving faster than most fighters while flying too low for effective engagement by conventional high-altitude batteries. British 3.7-inch and American 90mm anti-aircraft guns, positioned along the coast, achieved initial kill rates below 20%. London faced systematic destruction from weapons that air defenses could not reliably intercept. Prime Minister Winston Churchill personally authorized use of proximity fuses against Von missiles, despite the risk of technology disclosure to German intelligence. Modified fuses were rushed into production at Crosley Corporation and flown across the Atlantic in specially configured Lancaster bombers, risking the aircraft and crews to deliver the ammunition Britain desperately needed. British anti-aircraft batteries along the coast began firing proximity-fused ammunition against incoming V-1s in mid-July 1944. The effect was immediate, dramatic, and overwhelming. During the first week of proximity fuse use, kill rates increased from 10% to 24%, By the second week, kill rates reached 48%. By the fourth week, 79% of V-1s were destroyed by proximity-fused anti-aircraft fire before reaching their targets. On August 28, 1944, radar detected 104 Vone missiles approaching England in a concentrated attack designed to overwhelm defences. Proximity-fused anti-aircraft guns destroyed 68. Of the remaining 36 that penetrated the coastal gun belt, fighter aircraft destroyed 32. Only 4 Vone missiles reached London that day. The British capital was saved by technology developed on the other side of the Atlantic and rushed into production specifically to counter a threat that conventional defences could not stop. Churchill later acknowledged that proximity fuses made in the United States proved potent against the Vone rockets that assailed Britain, noting that without this American technology, London would have faced far greater devastation. The Vone campaign demonstrated that proximity fuses could be used over land without compromising security if the tactical situation justified the risk. Thousands of fuses were fired over England, and inevitably some failed to detonate. German forces recovered several unexploded examples from crash sites and sent them to technical intelligence for analysis. German ordnance experts examined the fuses with instruments and X-ray equipment, attempting to understand their operating principles. But they concluded, incorrectly, that the fuses were some kind of advanced mechanical timing mechanism they did not fully comprehend. The possibility that shells contained miniature radio transmitters operating at microwave frequencies seemed beyond credible technology, given what German engineers understood about the forces involved in artillery launch. This failure of imagination proved as effective as any security measure. German intelligence never determined the true nature of proximity fuse technology, never developed effective countermeasures, and never replicated the design despite having captured examples in their possession. The secret remained secure not through perfect operational security, but through enemy disbelief that the technology could possibly exist as designed. The broader impact of proximity fuse technology extended beyond World War II into fundamental changes in military weapons development. The techniques pioneered for miniaturizing electronics and hardening components to survive high-G acceleration became foundational for subsequent advances in missile guidance systems, space exploration, and modern artillery. The concept of distributed intelligence, where individual munitions carry sophisticated sensors and processors capable of autonomous operation, traces directly to VT fuse development between 1940 and 1945. Modern smart munitions that can sense targets, discriminate between targets and decoys, and optimize detonation timing represent evolutionary development of principles established by Dr. Tuve and his team. Dr. Merle Tuve, returning to the Carnegie Institution after the war, rarely spoke publicly about his role developing proximity fuses. When details were finally declassified and released to the public, Tuve consistently deflected personal credit, emphasizing instead the contributions of hundreds of engineers and thousands of production workers who transformed theoretical concepts into millions of reliable fuses manufactured under impossible deadlines. His modesty understated his essential leadership in a program that War Department officials ranked second only to the atomic bomb in strategic importance to Allied victory. Without his insight that radio proximity detection could be miniaturized sufficiently for artillery shells, without his persistence through countless early failures when success seemed theoretically impossible, the proximity fuse would have remained an interesting concept rather than combat reality that killed tens of thousands of enemy personnel. The production achievement equaled the technical accomplishment in scale and complexity, manufacturing 22 million proximity fuses, each containing 130 precision, components assembled to tolerances measured in thousandths of an inch, required industrial organization on unprecedented scale. Over 100 factories had to coordinate delivery of components matching exact specifications while maintaining absolute secrecy about the final product's purpose. Supply chains delivered vacuum tubes, batteries, resistors, capacitors, and electronic components from hundreds of specialized suppliers, all synchronized to keep assembly lines operating at capacity without interruption. At 70,000 fuses per day during peak production in 1945, the program required manufacturing and assembling approximately 9 billion total electronic components over the course of the war. The cost per fuse dropped dramatically as production techniques improved and economies of scale took effect. Early fuses in 1942 cost $732 each. By 1945, mass production had reduced unit cost to just $18 per fuse, representing a 97.5% cost reduction while simultaneously improving reliability from 50% to over 90%. At $18 per fuse, the weapon remained expensive compared to conventional mechanical fuses, costing less than $2. But the increased lethality justified the cost differential. A proximity-fused shell was worth 5 to 10 conventional shells in terms of target effect. Since the shell itself cost the same regardless of fuse type, paying extra for a fuse that multiplied effectiveness represented obvious value to military planners managing ammunition expenditures. Secretary of the Navy James Forrestal stated after the war that the proximity fuse helped blaze the trail to Japan, noting that without the protection this device provided to surface ships, the westward advance across the Pacific could not have been so swift, and the cost in men and ships would have been immeasurably greater. His assessment reflected command-level understanding of how proximity fuses had enabled aggressive carrier operations deep into Japanese-controlled waters. Admiral Arleigh Burke, who served as Chief of Staff to Admiral Mark Mitcher commanding fast carrier task forces during 1944 and 1945, recalled that all 5-inch ammunition carried by fleet units in the final year of war was fitted with proximity fuses. Those fuses, he stated, knocked down enemy planes by the dozens, preventing ship losses and casualties that would have been enormously larger without this technological advantage. British Prime Minister Winston Churchill, reflecting on the war years, specifically noted that proximity fuses manufactured in the United States proved potent against Vone rockets that assailed Britain in 1944 and likely saved London from devastation that would have exceeded the Blitz. His acknowledgement recognized American industrial contribution to British survival during one of the war's most dangerous periods. The Japanese never fully understood why American anti-aircraft effectiveness had increased so dramatically after early 1943. Post-war interrogations of Japanese military officials and technical experts revealed that most believed Americans had developed vastly superior fire control radar or had integrated aircraft detection with gun directors in ways Japanese technology could not match. Some Japanese engineers speculated about radio-controlled shells that might receive guidance signals from ships, but dismissed the concept as technically impractical given the number of aircraft and the limited radio frequencies available. The idea that individual shells could carry complete miniaturized radar systems capable of autonomous target detection seemed beyond credible technology given Japanese understanding of electronics and the forces involved in gun launch. This comprehensive failure of imagination allowed the proximity fuse to remain operationally secret throughout the war, despite thousands of fuses being fired in combat where Japanese forces could observe their effects. The psychological impact on Japanese aviators of facing weapons they could not understand or effectively counter contributed to the erosion of morale that made kamikaze tactics seem acceptable by 1945. The proximity fuse stands alongside radar and penicillin as technologies that materially affected World War II's outcome through direct application to combat operations. Unlike radar, whose development occurred simultaneously in multiple countries through parallel research efforts, the proximity fuse resulted from deliberate, focused application of existing scientific knowledge to a specific military problem identified as critical. Dr. Tuve and his team at Section T identified what needed to be accomplished, determined how to achieve it through systematic engineering development, and executed a program that achieved operational capability in under 3 years from initial concept to combat deployment. This focused approach to weapons development became the organizational model for Cold War military research programs. The Manhattan Project, developing atomic weapons, followed similar organizational patterns of university laboratories, industrial contractors, and military oversight, working towards specific technical objectives under compressed timelines. Post-war missile programs adopted the same structure that had proven successful for proximity fuse development. The legacy of those 20,000 G-rated fuses extends beyond their direct combat effectiveness into how nations organize scientific talent for military objectives, how industries manufacture precision electronics at scale, and how seemingly impossible technical challenges yield to sustained effort backed by adequate resources and clear priorities. The miniaturized vacuum tubes that seemed impossible in 1940 became routine by 1945. The precision manufacturing that initially required specialized technicians became increasingly automated as production techniques advanced and quality control methods improved. But in 1943, 1944, and 1945, as Japanese aircraft fell from the sky over Pacific atolls, as Vone missiles disintegrated over the English Channel, the proximity fuse represented the absolute cutting edge of what human ingenuity could achieve under wartime pressure. Lieutenant Red Cochran, watching that first Japanese Val dive bomber disintegrate on January 5, 1943 off Guadalcanal, understood immediately that something fundamental had changed in aerial combat. His gun crew had destroyed an aircraft without perfect aim, without precise manual fuse setting, without any of the complex calculations that had limited anti-aircraft effectiveness for decades. The shell had performed the work autonomously, sensing the target, timing its own detonation, achieving what human gunners could only approximate through volume of fire and probability. In that moment in the Solomon Islands, a new era in warfare had begun. The age when individual munitions carried sufficient intelligence for autonomous operation had arrived. The trajectory would lead through guided missiles, smart bombs, and eventually to weapons systems that could identify and engage targets with minimal human intervention. All of these developments traced their conceptual lineage to those first proximity fuses that changed naval warfare in the Pacific. Commander Hall, standing on Hadley's damaged bridge on May 11, 1945, watching the last attacking aircraft fall into the sea, understood the same truth Cochrane had grasped 2 years earlier. His ship had survived impossible odds not through luck or individual heroism, though both played roles, but through technology that multiplied the effectiveness of every shell fired. Proximity fuses had not made his ship invulnerable. They had made survival possible when survival should have been mathematically impossible. The story of the proximity fuse proves that sometimes the greatest victories come not from individual genius, but from collective effort, not from seeking impossible superweapons, but from making practical solutions work reliably at scale, not from desperate gambles, but from systematic engineering, applied with unlimited resources and unwavering determination toward clearly defined objectives. German soldiers and Japanese airmen who faced proximity fuses never fully understood what killed them with such devastating effectiveness. They reported only that American defenses had become impossibly accurate, that ships seemed able to shoot down aircraft regardless of maneuvering or altitude, that artillery created explosions that appeared to seek targets with supernatural precision. The technology remained mysterious, the principles incomprehensible, the implications terrifying. The proximity fuse did not win the war alone, no single technology ever does, but it contributed to Allied victory in ways that saved thousands of American and British lives, accelerated Axis defeat by making aerial offensive operations unsustainable against well-defended targets, and demonstrated the decisive advantage that scientific innovation backed by industrial capacity could provide in modern warfare. Those 20,000 G-rated fuses, each representing the technological limits of 1940s electronics and manufacturing, turned American anti-aircraft artillery into weapon systems that enemy forces never anticipated and could never effectively counter, even when they captured intact examples and subjected them to technical analysis. They remain a testament to what free societies can achieve when scientific curiosity, industrial capacity, and strategic necessity a line in pursuit of objectives worthy of extraordinary national effort. The proximity fuse demonstrated that the impossible becomes possible when talented people receive adequate resources, clear missions, and the freedom to pursue solutions through systematic experimentation and engineering discipline rather than ideological constraints or bureaucratic interference. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.